started again. Welcome back. 8.3 is a section on trigonometric integrals. So in this section, we're mostly going to be focusing on integrals of the following two forms. The first form is this integral of sine to the m power times cosine to the n power dx. Okay, where m and n are both um, this symbol means integers, and this little plus sign here means positive integers. So whenever you see me write something like this, I'm just abbreviating positive integers. So positive whole numbers, we're not going to have to worry about fractions. Most of the time, we're not really going to have to worry about negative integer exponents, but sometimes that comes up, and we should know how to handle that. So as we approach those problems, we'll cross that bridge when we get there, right? And then we'll also look at some problems of the form the integral of secant to the m power x times tangent to the n power of x dx. Okay, that's very similar to this guy up here, except we're using two different trigonometric functions here that are being multiplied and they have different powers. So to start off, when we're using or sort of approaching problems of this form with the sine and the cosine of different powers, then there are a few trig identities that are going to be really helpful. First, we have sine squared of x plus cosine squared of x equals 1. That's our standard Pythagorean identity, right, which gets its namesake from the Pythagorean theorem. Then we have these two sort of formulas down here that we can think of as power reducing formulas. So if we ever have a sine squared of x and we want to bring that exponent power down, then we can sort of convert that to 1 minus cosine of 2x, where the angle inside of the function changes all over 2. So this is the power reducing identity for sine squared x. And then this formula down here, obviously we start with a cosine squared, and this would be the power reducing formula for cosine squared x. Okay. And I'm going to erase this so you can see the 2 a little bit clearer. So those three identities are going to be kind of the workhorses if we ever need to sort of manipulate our integrand, right? The expression that's in the integral, so that we can get these integrals in a form that's going to be really nice to integrate. Okay. So let's look at our guidelines for approaching an integral of this form, the powers of sine and the powers of cosine. Okay. So there's three situations that we really want to watch out for, and I've sort of labeled them A, B, and C. So given an integral of the form, the integral of sine to the m power of x times cosine to the n power of x dx, if m is odd, then m should be defined as 2k plus 1. This here is just a standard definition of an odd integer. Right, so if you've never seen this before, then you should realize that the even integers are defined as, let's call it e is equal to just 2k, where k is some integer. Okay, and I will call this odd. I'm going to call it O, not 0, is just 2k plus 1, where k is some arbitrary parameter and it has to be an integer so that we are dealing with whole numbers here. But the idea is that like the definition of an even number is that it's divisible by 2. That's why we have a factor of 2 here. And then an odd number is just going to be that even number. And then if you just add 1 on the number line, you'll get to an odd. So that's why they're defined that way. If you've never seen it, then we're kind of going to play around with this 2k plus 1 whenever we're talking about an odd power of sine or cosine. Okay, so I'm going to take that off. And so the key for evaluating or integrating an expression like this is that we want to save a factor of sine x so that we can define du to be equal to sine x dx. Okay, and then we'll convert the remaining factors to cosines, and then it should just be a straightforward u substitution problem. Okay, so let's take a look at this first example. Here, notice that we have an odd power of sine, right? And this strategy is saying, okay, well, if we have an odd power of sine, what we want to do is kind of break out a factor of sine x so that we can sort of move that to the back of the integral next to the dx, and we'll define that as du. Okay, so I'm going to rewrite this integral as, and actually, I'm just going to, let's call this, I'm going to kind of rearrange it. I'm going to put the cosine to the 4th power of x first. Then I'm going to break up this sine to the 3rd power so that it's now times sine squared x times sine of x, right? There's my 3 sines, dx. And we wanted to reserve this sine x dx so that that would be du. Okay. Now I said that some trig identities were going to be really useful here. So the useful trig identity is that this sine squared x, if you recall from your Pythagorean identity, sine squared x plus cosine squared x equals 1. If we just rearrange this, we can get sine squared x is equal to 1 minus cosine squared x, right? So we can make this replacement so that our integral, once we replace this guy, will only be in terms of cosines. Okay. So we'll have cosine to the 4th power of x times 1 minus cosine squared x times sine of x dx. Then with a little bit of algebra here, we're just going to distribute this cosine to the 4th power of x here and here so that we get this new integral, which says we have cosine to the 4th power of x minus cosine to the 6th power of x, because when you multiply powers, you add the powers. And I'm just putting this in brackets for clarity's sake. Maybe it'll be clear in a second. And then we have that sine of x dx. And now we're ready to do our u substitution, because if this sine of x dx is what we're calling du, then cosine is going to be our u. So we're going to let u equal cosine of x, right? So that means that if we do that u substitution and we actually compute du, then this should be negative sine of x dx. Are you guys okay with that? Right, so you do have to watch out for these signs, because like the guideline suggests that we want to keep one of these sine x dx's as our du, but that might not literally be the case since we have this negative sign. What we actually ended up getting was negative du is equal to sine x dx. So when we make this replacement, this guy will partly go here, and what I'll do is just say, well, we're just going to pull that negative out of the integral. So I'm just putting that in the very front of the integral, and we should have something du, right? So we have our negative sign and our du, that's our negative du. And then since cosine is u, well, this is just going to be u to the fourth power minus u to the sixth power du. And then that's just a really easy polynomial that we can integrate, right? So once we do that, we'll have negative, then this will be 1/5 u to the fifth power, uh, minus 1/7 u to the seventh power. I'm just going to put our plus c out here since it's an indefinite integral. And then we can substitute our cosines back in, right? Substitute u back in. So we should have, and don't mind me if I do this, I'm going to go ahead and also distribute this negative sign that's on the outside of these brackets. What we should have is negative 1/5 cosine to the fifth power of x plus, because a negative times a negative gives you a positive, and that'll be 1/7 cosine to the seventh power of x plus c. And so there is our indefinite integral. Maybe it's a bit much for a Monday morning, but how are you guys feeling about that problem? Not too bad, right? And maybe I was a little bit wordy earlier, but this is exactly what I was talking about, where like if you can make that, you just follow the guideline and make that appropriate substitution, then we're really just dealing with the U substitution. Okay. So that's going to be the first thing. Just, make sure that when you start going through some of these practice problems, have these guidelines with you because it's going to take some practice with them before you start committing them to memory. And then once you commit some of them to memory, you'll start to realize like, oh, okay, I can speed up a little bit now, right? I'm not having to go back and forth and read the guideline every single time. But if that sign, the power of sine was odd, then we're breaking out a factor of sine x dx so that that can be our du. Okay. All right. Mm. So now we'll look at a situation where what if the cosine power is odd, right? So we're still looking at an integral of the same form, and maybe that's the thing that's going to be a little bit confusing is that they look very similar, but we really need to pay attention to which of these powers is odd. Is the power of the sine odd or is the power of the cosine odd? Okay. So if n, the power of the cosine, is odd, then that means that we'll have this n is equal to 2k plus 1. And this plus 1, you can think about it is like that's the extra factor of that trig function that we're breaking out of the problem. So we always end up having something like cosine. You could think of this as cosine squared, but it could be like a multiple of squaring, like to the second power, fourth power, sixth power, what have you. So we're always going to break that up, and then we would have an extra cosine here in the function, and that would be the plus one, that extra. Okay. So the key for these kinds of problems where our power of cosine is odd is that we want to save one of the factors of cosine so that du can be defined as cosine x dx. And then we'll convert the remaining factors to sines, and then it should be a pretty straightforward u substitution. Okay. So this one's going to be a definite integral. And there's a couple of different ways that you could sort of process this, but I'm going to just start off like this. Start off by writing down our limits of integration, pi over 6 to pi to the third. And then I'm going to get lazy after this point and stop writing those limits, right? So if I do forget at the end, putting you guys in charge of reminding me to actually evaluate the integral. I'm going to write this as cosine to the third power of x times sine to the negative 1/2 power. Actually, I don't like this notation. Not negative 1/2 power. What I'm going to do is call that sine of x to the negative 1/2 power like that, dx. Now, have I lost anybody by putting this as sine of x to the negative 1/2 power? You guys understand that that's a root, right? Okay. I'm just gonna step over here for a second, grab my calculator so that we have it when the time comes. All right. So this guideline says what we want to do if our cosine has an odd power is break out one of those factors of cosine, sort of marry it to the dx so that that can be du. So we'll rewrite this. Again, I'm going to be lazy and drop my limits of integration till the end now, but we'll have a cosine squared x there times, I'm going to leave this as sine of x to the negative 1/2 power. But now we'll have that extra cosine of x dx, and this is the thing that we want to call du, which means we want to write everything in terms of sines. So for this guy over here, we want to use an identity. And whenever I'm seeing a cosine squared, I'm thinking to myself, let's go ahead and try the Pythagorean identity there. So if we go over here to the side, remember the Pythagorean identity, then that means cosine squared of x plus sine squared of x is equal to 1. So cosine squared of x is equal to 1 minus sine squared of x. Okay. And like at a certain point, I'm probably going to stop writing this like algebra where I write down the original Pythagorean identity and kind of subtract something over to the other side. Because I'm going to assume that you guys can do that in your head. Okay. So if I ever sort of lose you by doing that, just, stop me and ask me what happened here. Because all we're doing now is writing this as 1 minus sine squared of x times sine of x to the negative 1/2 power and times this stuff over here, which cosine of x dx. Now we're ready to make our u substitution, right? So u is just going to be equal to sine of x, so that our du is just equal to cosine of x dx. Once we have those definitions down, we can go back in here and say this is 1 minus u squared times u to the negative 1/2 power times du, and we got just straight up du there, so we didn't have to worry about any negative signs or any other factors that we're sort of dividing out with that substitution. So now let's go ahead and distribute this. Since this is just like a polynomial in terms of u, we should have the integral of, we sort of FOIL this out, u to the negative 1/2 power minus u to the 2 would be what? 2 is equal to 4 over 2 minus 1/2, which would be 3 over 2. So this is going to be the 3/2 power du. I'm just going to bubble this in because we could have done that in the calculator. The fractions were throwing me for a second, so I needed to see it all written out. And let me zoom in if you guys can't see that. I'm just going to put here fraction. Any questions, comments about that simplification? Because now we can go ahead and integrate, and this should be pretty straightforward. So equals, if we add 1 here, we'll get u to the 1/2 power divided by 1/2, which would mean we have a factor of 2 there, right? Because now we're flipping that to the reciprocal. Minus, if we add 1 to this guy, that would be adding 2 over 2. So it would be u to the 5 over 2, which means 5 over 2 would be the denominator, and that will flip to, sorry, 2/5 for our coefficient plus c. Questions, comments? Oh yeah, not plus c, right? Because we're not doing an indefinite integral, right? We're not looking at a family of functions. We're actually going to evaluate this, but we'll go ahead and do that on the next page since I've run out of space here. Okay, so this will be 2 sine to the 1/2 power, and this will be negative 2/5 sine to the 5 over 2 power. Let's see what that looks like. We said 2 sine of x to the 1/2 power minus 2/5 sine of x to the 5/2 power. And we're going to evaluate that from pi over 6 to pi over 3. And you could do this obviously in the calculator. I really, whenever I'm dealing with trig functions, this is just my personal preference. I kind of don't like having trig functions with these fractional powers. So like if you wanted to convert this to 2 square root of sine x minus 2/5, and then this is going to be the square root of sine x to the 5th power. I don't know if that's any easier for you guys to sort of process in your brains, but to me, there are like fewer numbers going on there, but I'm just going to go ahead and process this in the calculator, right? Let's just get an approximate solution here to 3 decimal places. I think we'll be fine. So now in one of my previous videos, I think from, I don't know if it was like 7.6, whenever I gave you guys that video on planar lamina and finding the center of mass, I started doing this thing in my calculator. And I'm not sure if you guys are aware of this, but um, if I need to evaluate an integral, we start off with this number at the top. So in my calculator, I'm going to put pi over 3 and then press the store button to store that as our variable x. Because now x is going to be that value. It's going to be pi over 3, right? So in doing that, now I can just type in exactly this function, hit enter, and it's going to give me the first value that we're going to then subtract from. So we'll just do 2 times the square root of sine x, and the calculator is storing pi over 3 as x, minus 2/5, and then we have the square root of, let's go with sine x again, but then we're going to raise that to the 5th power, and we get this number. So we'll have 1.582. I'm going to go out to 4 digits there, minus, and then we'll go ahead and store pi over 6 as x, and then do this whole thing again. So the nice thing about using the calculator this way is that now we can say, okay, pi divided by 6 is going to be stored as x. So we have our new definition for x. And then if we didn't clear the calculator, we can just go back up to this function, which has been typed in terms of x. But now that x is set to be pi over 6, we can just hit enter and we'll get a different value. So this is going to be minus 1.3435. And so if we know that we're taking this definite integral, we can go back up to our 1.582, which is here if you want more decimal places, and then just simply subtract this new thing that we got, the 1.3435. And so our answer would be 0.23, and I'm going to round that to 3 decimal places. That's 9. I'm going to put a little squiggly equal sign here because that should be the approximate value of our integral. One other note here is that if you're going to store pi over 3 or pi over 6 as x. Uh, Make sure your calculator is in radians mode. I mean, I kind of feel like after you get out of pre-cal, everything is in radians. So, um, on the off chance that you change the mode to degrees, just make sure that you're checking that mode and making sure you're in radians before you do this kind of calculation. So, questions, comments? How's that feel? You guys ready for the next one? You guys are just drinking from the fire hydrant every single day, right? Oh, Mark is asking in the chat, do we need to clear the X for future problems from the calculator? Um, mm, well, yes. The answer to that question is like right now, if I were to like just turn off my calculator and turn it back on, the memory is still storing it as the last value that I put in there. So if I type X, you get this decimal, which um should be doesn't look like it's either one of those values. No, sorry. It is one of those values, right? It was the pi over 6, right? And that was the last thing that I put into the calculator. So what you might not realize is that if you were to clear the memory of your calculator and you just type x equals, it's stored at 0 as a default. So if you want to put it back and set it to 0, that's fine. But like each and every single one of these problems where you have a definite integral, you're going to have different limits of integration. So it doesn't really matter as long as you set the new x value correctly. It'll just overwrite the previous one that was saved. Okay. And I mean, this is a good opportunity for me to sort of talk mess about some of my younger students that are in college algebra. They kind of always want to do things in the calculator. And so when they're evaluating expressions, they're just typing in the x's into the calculator, not knowing that like in a particular problem, x might not be equal to 0. But the calculator defaults it that way. And so they're getting an answer and thinking that they're correct, but that's not even what the problem sort of calls for, right? X might be defined to be another value, or you're actually having to solve the equation to find the value of x. So, um, for you guys, I think it's pretty obvious. Like that's just a placeholder. That variable is just a placeholder. It's stored as 0 as a default, but you can change that value to be anything. It will store the last entry and keep that until you clear the calculator's memory. Okay, so it's not really, Mark, I don't think that's going to be a problem as long as you're clearly defining your x's when you evaluate these definite integrals. And hopefully that answered your question. Okay. Yeah, no, thank you. Because sometimes I need to take a break from these problems too. If you guys just want to gung ho, just jump into every single problem, I'm like, God damn, I need to catch my breath a little bit. All right, so let's move on to the next problem then. So the last guideline that they give us for this type of integral, we're dealing with sine and cosine powers, um, is that when both m and n are even non-negative powers, what we want to do is make repeated use of those power reducing formulas, those trig identities that were given here on the first page. Okay. Once we do that, then we want to try to rewrite our integrand into odd powers of cosine. Okay. Because if everything is written in odd powers of cosine, then we can proceed with our guideline for method B, where we can break out that extra cosine and define du to be cosine x dx. Okay. So here, we're just given the integral of cosine to the fourth power of x dx. There's no sine here. So I will bring back the power reducing formula here. So for cosine, the power reducing formula of cosine squared x is equal to 1 plus cosine, and then the angle changes to a double angle, so 2x inside the cosine over 2. Okay. So the first thing I would do with something like this is write my integral symbol, and then cosine to the fourth power of x dx is the same thing as, well, let me write it out like this first. Cosine squared x times cosine squared x dx. Okay, so that means we're going to use this power reducing formula for each of the cosine squared x's. So this is going to look really ugly at first, but let's go ahead and write this down. 1 plus cosine of 2x all over 2. That's our first cosine. Then our second cosine will be the exact same thing. So 1 plus cosine of 2x all over 2 dx. To make some of this algebra a little bit cleaner for us, whenever we're dividing by 2, that's the same thing as multiplying by 1/2, right? And since we're basically multiplying by 2 factors of 1/2, we can pull out a factor of 1/4 from the integral so that we just have 1 plus cosine 2x times that 1 plus cosine of 2x. That, make sure the color coordination is on point. There we go. Dx. And now we need to FOIL this out. Okay. So we're going to get 1/4 integral of, this should be 1 times 1, which is 1 squared. And then we have plus 1 times cosine of 2x. And then another cosine of 2x. So that's going to be 2 cosine of 2x. Plus, then we will have a cosine squared of 2x dx. I'm going to take a strategic sip of water because I see you guys writing. Okay. Now, if you look at these terms in the brackets here, um, individually, these first two terms we could integrate really nicely. But this one's going to be an even power of cosine. So we would have to do another round of a power reducing formula here. Okay. What I'm going to do to make this maybe a little bit easier for us, I don't know if it's easier, guys. These are long problems, right? They're tedious. Is I'm going to say that this is 1/4 times the integral of, you could write 1 dx, but I'm just going to write dx. Plus, if I distribute the 1/4 here times 2, that's going to be 1/2 times the integral of cosine 2x dx. So that's going to take care of these two guys. Plus, then we have a 1/4 times the integral of cosine squared of 2x dx. So these are 3 integrals, and this guy over here is going to need another round of power reduction, right? But we do know what the integral of 1/4 of what the integral of dx is, right? That should just be 1/4 x. You guys okay with that? So that's going to be 1/4 x plus, we can do the integral here. Any ideas what this is going to integrate into? Just want to give you guys a chance to sort of take a crack at it. How do we integrate something that looks like this? Like if this was just a cosine x, do we have a formula for integrating cosine of x? What would that be? I think it's just sine. Yeah, I don't think it's going to be a negative. But what we would do is like a little round of u substitution, right? If u is equal to 2x, that means that du is equal to 2 dx, right? So what we need to remember is that we're going to be dividing out a factor of 1/2 when we do this. So what we would have is this factor of 1/2 here. And when we integrate this guy, we'll have another factor of 1/2 from the du. And then that will just be sine of 2x when we actually integrate that. So this is going to turn it out to be like a 1/4 sine of 2x. So as we're learning sort of more sophisticated techniques that involve some more processing, we need to make sure that we're not losing track of kind of the simpler looking integrals, that one was just a basic u substitution. And it really does help to be able to say like, okay, well, if this has a 2 in there, when I integrate it, I know I'm going to take out a power of 1/2 if the u substitution works, right? But then we still have to deal with this guy over here, which is the 1/4 integral of cosine with an even power of 2x dx. So we're going to take that to the next page. I think I got a blank page over here. So let's see. What we have so far is the 1/4 x plus, I believe. Let's go back over there and look at it. 1/4 sine 2x. And I think this was a plus also, a 1/4 times the integral of cosine squared of 2x dx. Nobody can see what I'm writing. Just going to double check to make sure that we wrote that correctly. 1/4 x, 1/4 sine 2x, 1/4 cosine power, so cosine squared 2x. Okay. That look good? Okay. Well, now let's take this guy and reduce its power. That is a weird looking power. It is what it is. So now, because I'm going to get incredibly lazy, I'm just going to put, these guys are going to keep following us. Plus 1/4. And then this will be 1 plus cosine 4x over 2 dx, which will be, we can factor out this 2 so that we have now 1/8 times, I'm just going to write this as dx because that's going to be a 1 dx plus, we have that 1/8 still on the outside once we factor that out. Integral of cosine 4x dx. And these guys are pretty straightforward to integrate. So this will be 1/8 x. I'll bring back in my 1/4 x over here, plus my 1/4 sine of 2x here. And the only reason I'm bringing those guys in is because these are like terms. So I'm just going to combine like terms. 1/4 plus 1/8 is going to be 3/8. 3/8 x plus 1/4 sine of 2x. And I haven't forgotten about this integral on the very end that we still need to integrate. So we're going to have plus 1/8. And if you think about this 4x and you set that to be u, then du is equal to 4dx, which means that we need to pull a factor of 1/4 out of this integral when we make that du substitution. Okay. So when we integrate that, that's going to be times our factor of 1/4 here. And then this will just be a sine of 4x, like so. So when we go ahead and multiply that out, we're going to have 1/32 sine to the 4x, or sine of 4x rather. And this was an indefinite integral, so we're just going to put a plus c and call it a day. So sort of to put a bow on that problem, I think that the one thing that might start to trip us up a little bit is those basic u substitutions that we're doing with these guys. Um, when we just have, sine or cosine to the power of 1, we have simple integration rules for that. So we can just apply those rules. Just remember, if you are taking the integral of something that has an interior function, then we need to make sure that we're doing a u substitution so that our integrals have the correct like factor or fraction that's pulled out of the integral. Okay. Any questions, comments about those three examples? Okay. Fun stuff. Well, I think that those three examples are going to be really nice. But now we're going to turn our attention to guidelines for integrating things of the form secant to the m power of x times tangent to the n power of x. And there are four situations that we have to watch out for in this particular subsection. And that is when the power of secant is even and positive, what we want to try to do is save a factor of secant squared x so that we can define du to be secant squared x, because secant squared x would just be the derivative of like tangent x, right? So in that case, we want to save a factor of secant squared x so that we can write our integral in terms of tangents. Okay. Then when we have a power of tangent that's odd and positive, then we want to break out one of those tangents so that we can combine it with the secant and have a secant tangent, right? A secant x times a tangent x factor, because secant times tangent is the derivative of what? I think that's the derivative of secant, right? We'll see in a second, right? If I need to pull up the derivative rules there. Because I think like also another thing at this point is that um, when we start getting like deep into trig identities and these different kinds of integrals that we're doing and then u substitution, it requires you to sort of like go back and forth in your mind on what are the rules for differentiation versus what are the rules for integration, and then we kind of get like a little bit mixed up. But secant tangent, um, in my head, when I was learning this in Cal 2 back when I was college, I always told myself secant seeks tangent. So like the derivative of secant would be secant times tangent. Okay. And then you can verify that by looking at your derivative fact sheet if we need to. Okay. So the third option here for case C is that when there are no secant factors, and the power of tangent is even and positive, then what we want to do is convert a tangent squared to a secant squared factor. And that's going to be done using the Pythagorean identity. And, when we get to that point, if we have an example that looks like that, then I will show you the basic algebra to sort of convert your Pythagorean identity into terms of tangents and secants. And then the final situation that you might land in is that some of these integrals will be of the form secant m of x dx, where the m is odd. So if you only have an integral in terms of odd powers of secant, then we're going to use integration by parts. Okay. So those are the rules. I'm going to let them kind of just hang in the air for a second, give those of you that are in Zoom an opportunity to kind of write them down. Also give myself a little bit of a break. And then we'll take a look at our first example, which I have not written down yet. So let's write this down. Find the integral of tangent to the third power of x all over the square root of secant x dx. Okay. Now, for those of you in Zoom land that are like struggling to write this really quickly, just remember I will post this video later so you can pause it here so that you can write down those rules or those guidelines, but we'll see them played out here in the next problem. But I want to make sure we have enough time to go through some of these examples. I will keep on pulling the guidelines over here just so that we're kind of walking through them correctly. So, given this problem, find the integral tangent to the third power of x over the square root of secant x dx. Okay. Which of these guidelines looks the most appropriate for this kind of a problem? And what we might do is just like kind of go through the guidelines and say, okay, well, what does it require? The guideline A for this kind of integral says secant, the power must be even. Well, if we just have a secant x down here, that's a 1, right? So that would be odd. That's not going to be helpful here. This one, guideline B says the power of tangent is odd, right? So that one probably will work here. The third one says this is our guideline for when there are no secant factors. That means that we just have even powers of tangent, then we would do this one, and that's not the situation we're dealing with. And then this last one is when we only have secant and we have an odd power there. So I'm thinking that for this one, guideline B is going to be our best bet. Okay. So I'll keep that over here on the side, and we'll go ahead and sort of trudge our way slowly through this problem, where I'm going to write this as the integral of tangent to the third power of x times, and then I hate having these fractions with these roots, so I'm going to write this as secant of x to the negative 1/2 power dx. And guideline B says if the power of tangent x is odd, then what we want to do is sort of save a secant x times tangent x factor so that that can be our du, right? So if we're following that guideline, what do we want to do here? We could write this as tangent squared of x times, now I'm breaking this up, an extra tangent of x times secant of x to the negative 1/2 power dx. Well, this doesn't really feel nice, does it? What could we do here? Okay, well, I'm gonna do something maybe a little crazy over here. We have secant to the negative 1/2 power. What could we do here? Power of the odd. We want that, and we want the remaining powers in terms of secants. Okay, let's do this. Let's take this tangent squared x, right? And for our Pythagorean identity, the standard Pythagorean identity says sine squared x plus cosine squared x is equal to 1, right? And if I want to get a tangent, that would be sine over cosine. So I'm just going to divide everything by cosine squared x. So that now this becomes tangent squared of x plus 1 is equal to secant squared of x. And that means that tangent squared of x is equal to secant squared of x minus 1. Are you guys okay with that? Because like there we were hitting a roadblock, but now we're going to have this secant squared of x minus 1 replacing this guy here. So we're taking the integral of secant squared of x minus 1. And I'm going to kind of rearrange this. I know that maybe the rearranging gets a little bit overwhelming or disorienting. I'm going to put the secant x to the negative 1/2 power here, and I'll move the tangent just temporarily to the back with the dx, right? Because now that everything is in terms of tangent, I'm sorry, secant rather, we can just distribute that secant to the negative 1/2 power in. So we'll have, if we have 2 minus a half, that's going to be 3/2, right? So secant of x to the 3/2 power minus secant of x to the negative 1/2 power. And then that is going to be times tangent x dx. And these guys, you might put in a bracket here. How are y'all feeling? Okay. Because what we really need is to have this secant tangent, right? For our du, which means that we need to factor out a secant from these guys. So I'm going to write that secant out here, secant of x. This is the one that I'm factoring out. And when you factor something out, you're dividing that out of these original terms. Okay. So like you're multiplying it on the outside, but then you're dividing it out from the inside. So if I divided this by a secant x and divided this by a secant x, then in the brackets, what I'm doing is subtracting the powers here. And since this is a secant to the 1 power, you can think of that as a 2 over 2. What I will end up with inside is a secant of x to the 1/2, because 3 over 2 minus 2 over 2 would be 1 over 2, minus secant x. And then if I subtract 2 over 2 from this power, I would have a negative 3 over 2, like so. Still got my integral, still got my tangent x dx. So here I'm just going to make a note that these were weird powers, but we needed to factor out a secant x, which is the same thing as secant x to the 2 over 2 power, right? Or to the 1 power. So now that we have that, we've done all this kind of algebraic preparation. This secant tangent is what we want to define to be our du, which means u should be equal to secant x, such that du is equal to secant x tangent x dx. And so we can make this substitution. So now we have the integral of maybe not pretty at first, but now it should kind of be not the ugliest polynomial we've ever seen. This is going to be u to the 1/2 power minus u to the negative 3/2 power du. And again, thankfully, we didn't have any kind of factor or negative sign that we had to take out of this. We just had that straight substitution of du. So when we integrate this, shouldn't be too terrible. U is equal to, if we add 1 to this, we'll have 3 over 2, and then we'll have 2/3 as our coefficient there, minus this one will add 2 over 2, so that should be u to the negative 1 over 2 power, which means that we're going to have a factor of negative 2 in front of this guy. And this was just an indefinite integral, so we'll have a plus c there. So let's go ahead and put this back together. 2/3, what do we call u? Secant of x to the 3 over 2 power plus 2 secant x to the 1 over 2 power plus c. And as I said before, I kind of prefer having that in terms of roots, but I think I'm far too exhausted from the basic algebra there that we're just going to leave that as it lies. And I'm forgetting something, and that's that this is a negative 1/2 power. Questions, comments, just a general vibe check. How did that one feel? Did it feel exhausting? Yeah. What to you guys seems to be like the roughest part of this problem? Yeah. Remembering the identities. And so I just think like it's useful every now and then to just play around with those identities, especially the Pythagorean identity, right? Because you can get a whole lot of things from the Pythagorean identity. Um, as long as you remember like some basic identities for trig functions. So for instance, let me just maybe add this additional note here. For trig IDs, I always, in my head, when I'm working on these kinds of problems, ask myself, well, what are the most important identities to know? And I don't know if there's like a ranking that mathematicians do for these identities, but like the first most basic ones are like um, the triangle identities, which are like that sine of x is equal to um, triangle identities. I always write SOHCAHTOA to remind myself. Did you guys ever learn SOHCAHTOA? Right. So like it's not something that off the top of my head I'm going to be able to spit out. I'm sure that there's a lot of students that can, but I always have to write out SOHCAHTOA so that I remember that it's opposite over hypotenuse, right? And if we're talking about cosine of x, that's going to be adjacent over hypotenuse, which these triangle identities also convert themselves to those identities on the unit circle. This is really just a crash course in pre-cal, right? So like if we're looking at a unit circle, and I'm just gonna do my best here to do a circle. That's the worst circle I've ever seen. Okay. Then if you think about like just drawing an angle here in the first quadrant, right? Here's our angle theta, or really, let's call that x just to be consistent with the labeling I've already done over here. If we have this angle x, then the sine, maybe I shouldn't have done x because we like to call the coordinates on this x and y, right? So I'm going to go back here. Wish I'd used that erasable pen. I'm going to call these theta, right? For the angles. Are you guys okay with that? Right, so we have this angle theta in here. The x value here, the cosine of theta is just giving you the x value for any of these points here on the unit circle, right? Whereas this y value over here is just equal to your sine theta. And that's the same thing as saying, oh, this sine theta is going to be the opposite side divided by the hypotenuse, which, you could think of as the radius of the unit circle. And since that radius is 1, then that would be y divided by 1, right? Um, So those are like the basic definitions of sine, cosine, and then tangent is just kind of like this hodgepodge where you just have to remember that it's sine theta over cosine theta, right? But then once we have those, you can kind of build the sort of the dark identities, the what do we call them? The kind of reciprocal inverse functions for these trig functions. So the reciprocal trig functions, which it takes a little bit of memorization, that sine. If we turn this to 1 over sine theta, then we're going to get, what do we call that? Cosecant? Cosecant theta? You would love for that to be secant, right? Because like sine and secant sort of sound the same, but it's actually like the cosecant here. So when we take the reciprocal, we'll get that. And then the same thing for cosine here. If we take the reciprocal, 1 over cosine theta, then that's going to actually be our secant theta. And then from these, if we just kind of take the reciprocal of tangent, we would have cosine theta over sine theta. That's equal to our cotangent theta, right? But then, like, if you have these sort of six memorized, then we can play around with the Pythagorean identity, which again comes from the unit circle, but is our basic one sine squared theta plus cosine squared theta is equal to 1, right? Because, like, from this monster, we can kind of say, well, what if we divide by cosine squared theta? And we saw this already, right? If we divide everything by cosine squared theta, then sine divided by cosine would be tangent squared theta plus cosine divided by itself would be a 1. And then 1 over cosine squared, well, if we look at our reciprocal identity, that would be secant squared theta. So, like, that's how I was able to whip that one out, right? But if we took this over here and said, what if we divided by sine squared theta? Then we get a completely different identity, right? Because sine squared divided by sine squared would be a 1. Cosine squared divided by sine squared would be plus cotangent squared theta. And then 1 divided by a sine squared, if we go back to our reciprocal functions here, would be cosecant squared theta. So, like, from this one identity and the basic trig identities that are defined at the very beginning of pre-cal, right? You can sort of come up with these extra identities on the fly, right? So that you don't have to memorize them. And you might think to yourself, like, this is boring as hell. Like, I don't know why this is going to be useful. And it's like, okay, well, calculus 2 requires a lot of algebra. It requires you to do a lot of acrobatics with the trig function and their identities. So, like, if you can memorize the basic definitions of sine, cosine, tangent, if you remember the reciprocal definitions for cosecant, secant, and cotangent, and the Pythagorean identity, and can just, like, on the fly come up with these other identities, like, that will be helpful for sort of manipulating your integrals. That makes sense? Okay, so again, this was just a crash course review of some pre-cal stuff, but I think that doing a review from time to time is really helpful because maybe it takes some of the, I don't know, some of the magic, some of the fear away from these integrals that look really intimidating, right? Okay, so let's do the next example, and I think that maybe if it's not too bad, then we will call that a day because I'm not sure that we'll have much more time for extra examples. So let's call this example 5, and it's going to be finding the integral of secant to the fourth power of 3x tangent to the third power of 3x dx. Okay. Now, when we have these integrals where we have a function inside of the trig functions, we're going to want to be careful with our u substitution because we will get some multiplicative factors that we're going to have to take out of the integral at some point. But, like, let's look at our guidelines for these types of functions, right? So if we're dealing with functions that are the product of powers of secant and tangent, then the first guideline says when the power of secant is even and positive, which is what we have here, even and positive, then we want to save a factor of secant squared so that du is set to be secant squared dx. Okay. And then presumably we're just converting everything else into terms of tangent, right? So that tangent can be our u substitution. So let's kind of approach this and see what this is going to look like. So we said we wanted to save a secant squared. So I'm going to break this up into secant squared of 3x times, I'm going to put the tangent cubed of 3x here times, and then I'm going to put that extra secant squared of 3x with the dx, because this is what we want to call du, right? So then we want to turn everything in terms of tangent, right? But we have an identity for secant squared, right? And if I just bring back this set of identities that I have over here with secant squared, that's going to be tangent squared theta plus 1. So this guy here can be tangent squared of 3x, right? Because 3x happens to be playing the role of theta here, times tangent cubed 3x. And then we have our secant squared of 3x dx that shortly will be playing the role of du. Okay, well, we can actually just FOIL this out, right? So this will be tangent to the fifth power of 3x times that secant squared 3x dx. And now let's make our definitions, right? So we're going to go over here and say u is equal to tangent 3x. So that means that du is going to be the derivative of this, which would be secant squared 3x times, remember the chain rule here, right? Because if we have a function inside of another function, then the derivative is going to be the derivative of the outside function times the derivative of the inside function, which would just be times a 3 times a dx. Which means that I have to divide this 3 over to the other side. So I'm going to have 1/3 du is equal to secant squared x dx. So we can go ahead and make that substitution now, right? This is going to be a 1/3 on the outside of the integral. This all becomes du, and this is just u to the fifth power. What's up? Oh, yeah, yeah, yeah. 100%. Just me being lazy there. Secant squared 3x dx. Right? Just the 3's cancel out. This guy inside of the function cannot be canceled out with anything that's on the outside of the function. Okay. But yeah, good catch. So as far as we're concerned, though, like this is a really nice integral, right? Just turned into u to the fifth power. So we're going to call that 1/3 times u to the sixth divided by 6, or times 1/6, and then plus c. So this will be 3 times 6 is 18, 1/18. U is tangent to the sixth power of 3x plus c. And that should be it. Okay, you guys are gonna hate this. I made a mistake at the very beginning. Octavio, can you tell us where I made the mistake? Yeah, this guy should have been based on our trig identity here, tangent squared theta plus 1. Tangent squared of 3x plus 1 should have been right here. And then I should have distributed it there. So I should have had a couple of different terms in the integral. Okay. Now, I totally get that, like when there's like a big mistake that's made at the very end of the class, that it's like completely throws you off. But what I'm going to say is that this is wrong, and so we need to make a correction. Do you guys want to correct it right now, or do you want to say, oh, you guys can see the mistake and you'll correct it on your own later? Let's correct it right now. Okay, we have the time, so why not? Let's go back here and do the correction. So here we had secant squared times 3x times tangent cubed 3x, and then we had broken out our secant squared of 3x dx. This guy was playing the role of our du. My trig identity, and this is going to happen to you guys, so like I hope that you're not like judging me too harshly because then I would hope you don't judge yourself too harshly when you make mistakes. It happens. This should have then been tangent squared of 3x plus 1 times this tangent of 3 to the third power of 3x times secant squared 3x dx. But everything kind of proceeds the same. I would just say, like, let's go ahead and FOIL this out because the integral should have been our tangent to the fifth power of 3x plus our tangent to the third power of 3x times our secant squared 3x dx. Once the mistake was found, we can go ahead and make that correction pretty easily. U is equal to our tangent of 3x, which means du is still equal to secant squared of 3x times 3dx, which means we have 1/3 du is equal to secant squared 3x dx. And now I'm catching my breath and I'm trying to make sure that I don't have any additional mistakes, but I'm gonna phone a friend. How are we feeling about this so far? Have I made another mistake? Doesn't look like it, right? I don't think so either. I'm just starting to get paranoid, right? So again, I'm feeling the same feelings that you guys are. So once we make those substitutions, we should have u to the fifth power plus u to the third power du with a 1/3 on the outside. So this should have been 1/3, 1/6 u to the sixth plus 1/4 u to the fourth plus c. So distributing that 1/3, I should have the 1/18, and then this should be tangent, however you want to write it. You could write tangent with the little sixth power here of our 3x plus this will be 1/12 tangent to the fourth power of 3x plus c. And I think that is actually how it should have gone. 1/12 to the fourth power, 1/18 to the sixth power. Okay, yeah, that's perfect. This one's correct. Okay. So silly on my part to make that little incorrect substitution, but that's our Pythagorean ID substitution. And I think that's all I want to do with you guys today because I've probably spent all of your mental resources for this class. Okay. So if you have any questions later, I will be in Math World in the afternoon. I don't know if you guys are going to be on campus. For those of you that are not on campus, if you have any questions, shoot me a message in Canvas. Send me a screenshot of whatever it is that's giving you trouble. Just make sure that you send me those messages earlier rather than later, because if you message me at midnight, I am going to be dead asleep. Okay, so I won't get back to you until tomorrow. So we'll leave it at that. If you guys have any questions, just hit me up. But otherwise, I will see you guys on Wednesday.